with a new unit here, looking at a new coordinate system, that being the polar coordinate system. So we have been working with for a long time this rectangular coordinate system. So a coordinate system is a way of marking an object's location with respect to another location. So we often call this location we compare to, we often call it the origin, right? 0, 0. So with the rectangular coordinate system, if I have a coordinate out here, say x comma y, what we are actually saying when I say that this coordinate is x comma y, we are saying with respect to the origin, this location is x, this x distance horizontally, and then so x horizontally, and then y vertically. So hence rectangular system, going right or going right or left and then up and down. So this is, remember, this is just a simple position with respect to WRT, with respect to the origin. Okay, and in geometry, way back in geometry, you focus on dilating objects from a point other than 0, 0. That's a situation where you have your points with respect to something else. That's just translating back to geometry, but right here, right now, this is what we are most commonly familiar with. We're familiar with, if I say x comma y, that's a point that has an x horizontal distance and a y vertical distance. All right, so our new coordinate system. So the polar coordinate system. This system is another system to represent position with respect to an origin. So we call this origin now. We actually call this the pole. P-O-L-E, the pole of the hence polar coordinate system. So this is the pole, or we will know it as the origin. So you might hear me say the pole, you might hear me say origin in the following lesson, just know that that's what we're talking about. So if I have a point that is right here, rather than focusing on the horizontal movement and vertical movement, in polar system, we focus on two different things. We focus on first the direct distance. The direct distance an object is, we call this r, like radius maybe. And then, so we have this direct distance from the origin, and then we have the angle of turn, or the direction angle. Okay, so the coordinate would actually be r, the direct distance, comma, theta, whether we are in degree or whether we are in radian. So I'm just going to say this here. R is the direct distance to the pole, and then theta is our directed angle, or direction angle. You might think of that as that. As we just came from looking at vectors and parametric equations, we had direction angles. That's what we have here. Okay, the direction angles, where the angles are always measured from, they are always going to be measured from what we call the polar axis. So that's this horizontal axis, the polar axis. So the main difference is that we're not looking at a left, right, up and down movement. We're looking at a direct distance, a radius, and then the angle of turn from the x-axis, or we call it the polar axis. All right. So let's try plotting a couple points in this polar system. I want to say this. I could overlay this coordinate system on top of this rectangular coordinate system. I could place this r theta on top of an x and a y. So every x and y has an r and theta. And we're going to learn eventually how to transition from x comma y to r theta, but that's in the upcoming lessons. All right. So let's just start by plotting some points. Okay, so we have here an example of what a polar coordinate plane looks like. Rather than having what we always call the grid, we have a series of circles and these little rays that come out that mark our angle measures. So if we're looking at, say degrees, I would have 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and continue on. The same can be done in radians. So let's take for a moment that we want to plot the point 3, -45 degrees. Okay, so when we plot polar points, I recommend that you think of the degree first, and then plot the direct distance. So how we treat this degrees, this is -45. So the negative means rather than going counterclockwise, we're going to go clockwise. And 45 degrees is our middle ray. So 30, skip a line, 45, skip a line, 60. So we're on this ray. Okay, so we're on this ray. We do that first. Then 3 is the direct distance from the origin. So these little circles, there's 1, 2, 3. I just simply counted out 3. I go to this point and we are right there. Okay, so this is our point. Disregard that little dot. All right, so this is our point 3, -45 degrees, because we are a distance of 3 away from the origin, and we have an angle measure of -45 degrees. Okay, let's try another. So let's say we have the coordinate 1, 7 pi over 6. Okay, working with the angle measure first. Okay, so let's think of this. So we're in radians, so we have pi over 6. Okay, you use a technique that I like. 2 pi over 6 simplifies. 3 pi over 6 simplifies. 4 pi over 6 simplifies. 5 pi over 6 doesn't, so we're in the second quadrant here. 6 pi over 6 simplifies. 7 pi over 6 doesn't, so we are right here. Okay, so we're along this line. And then we have a direct distance from the origin on this ray. We're at a direct distance of 1, so we are in this first point. Okay, I drew the line for the direct distance and the angle measure, the little arrow for the angle measure, but we're not going to continue doing that. It's just that know that this point is 7 pi over 6 from 0, and then write this out. There we go. Just do that, and then we're 1 unit from the center. So let's try the next. So what if we have, say, -1 pi over 6? Take the approach of looking at the angle measure. So angle measure pi over 6. So that's in the first quadrant still. We are right here. Okay. So we're along this line. The direct distance is -1. So if it was +1, we would be right here. But what the -1 does is it says that we're 1 on the other side of the origin. So the negative, we go on the other side of the origin, but we have to make sure we stay along this line for pi over 6, so we are right here. What's interesting is that this point and this point give us the same position. Notice that 1, 7 pi over 6, -1 pi over 6 give us the same position. Now that was not possible in a rectangular system. If I plotted 3, -4, there was no other coordinate for that position. It was 3, -4. But now we're saying, oh, I have 1, 7 pi over 6. Okay, -1 pi over 6 represents the same thing. And there are many, many other possibilities to represent the same location. So before we talk more about that, remember, when plotting points, I'll make this little note here, when plotting points, read the angle first. Read the angle first. And the negative, when we have a direct distance that's negative, we go opposite of the origin, opposite of the pole. All right? So what would have been +1, we are -1. Put a little arrow, boop, there, like that. Okay? Let's look at how do we know, or how do we find the possible variations for a single position. So looking at that, that's our next title, is multiple representations of a polar coordinate. So, like I said, if I wanted to plot the point 3, 5, there is only one 3, 5 on a rectangular coordinate system. But let's say I want to plot, 5, 60 degrees. There are multiple representations of that position. Okay, so how we do this, how we think of this. One way of finding multiple representations, let's say I have R and the angle measure. One way is to maintain the same radius, but to add a full cycle onto your degree. So how we think of that is we have our theta. I said add, we could also subtract. So we're going to take our theta, whether in degree or whether in radians, and we add or subtract this. We subtract 2n pi, or it could be 360 here. 360 here. So here, 2n is simply a way of saying some even number. All right. So let's imagine for a moment we have the point 3, 7 pi over 4. All right, and I wish to find another representation of that position. So we can say that this is equivalent to. All right, keep the same radius. And we can add any even number of pi onto this. So let's just add, 2 pi. I can add 4 pi, 6 pi, or so on. Let's just add 2 pi. So we're going to say 7 pi over 4 plus 2 pi. And we're going to just have to simplify that. So this comes down to 3, all right, 7 pi over 4, 7 pi over 4 and 2 pi over 4. This would be 8 pi over 4. So 8 pi over 4 and 7 pi over 4 is 15 pi over 4. So these 2 points represent the same position in the polar coordinate system. All right, let's try another here. What if I had, say, -1 and pi over 6. So this is actually just an example we did. So we already know what one possible representation of that is. So we're going to say is equivalent to. So if we were to add 2 pi to this, we would get, I believe, example 2 on the other page. We would get +7 pi over 6. So we're going to take the approach of subtracting 2 pi just to see what happens. So we maintain the same radius, and we have pi over 6, and let's subtract 2 pi. All right, so that gives us -1. All right, so this is 12 pi over 6. 2 pi is 12 pi over 6. So 1 minus 12 is negative, I believe, -11 pi over 6. Is that right? 2 pi over 12 pi is, so 2 pi is 12 pi over 6. Yes. And 1/6 minus 12/6 is -11 pi over 6. Okay, so let's try, well, there's not much more to that. If I keep the same radius, I can add or subtract an even number of pi. So the other possibility is, let's say we have, r theta. I can get another representation if I have the opposite radius. So if I have positive r, we have negative r. And then having theta, rather than adding or subtracting an even number of pi, we are going to add or subtract an odd number of pi. So this 2n plus 1 is some odd number. Do this up. There we go. So let's look at an example. Okay, so let's say we have 2 and 2 pi over 3. Okay, so this whole process says another form of writing this position is saying negative 2 and then 2 pi over 3. Let's add an odd number of pi. So I can add 3 pi or 5 pi, but why not just add pi? Okay, so that would give us then negative 2. And then this would be 3 over 3. So 2 over 3 plus 3 over 3 is 5 pi over 3. There we go. So if we were to plot these 2 points, they would be at the same position. So remember, when plotting, we would use this angle measure. You would use this angle measure, go to that portion, that quadrant, and then with the direct distance of 2, that's 2 circles out, we have our point. So this one, I would have 5 pi over 3. So that would take me all the way to quadrant 4, but the negative radius says, oh, we go through the pole and 2 on the other side, and yes, that would give us to this position. Okay, so if you wanted to practice graphing them, I'm sure you have extra coordinate planes to work with. Before you began watching this video, you should have had some coordinate planes to use. So last example. So 3 pi over 4. Okay, so working through this, we can switch the sign, so 3 to negative 3, and then we already added pi, so why not test out subtracting pi? Okay, subtracting pi, that gives us negative 3. Okay, so this is 4 pi over 4, again the common denominator, so 4 over 4. 3 over 4 minus 4 over 4 is negative 1, so negative pi over 4. So we get another representation. And I can continue to do this. If you recognize, I could subtract 3 pi and get another representation. I can add 11 pi and get another representation. This is one big difference with the polar coordinate system, is that there's multiple representations for the same position, and we did not have that in the rectangular. So you should be practicing, after watching this quick lesson, you should be practicing how to plot and how to find other representations here. So good luck, and I will see you all in the next lesson.